Hello everyone. In the previous session, we have understood in detail about what a vector is and what a vector space is. We have also very well looked at how you represent your data in terms of vectors in a given vector space. So any vector in a given vector space can be represented with respect to different basis vectors that we have. We have not yet looked at what basis vectors are, and we are not aware of that particular concept yet, which we are going to discuss now. And then let's look at what are the different operations that one can perform on any given vectors that we have. All right. So let's say that we have three different vectors here called x hat, y hat, and z hat. Let me represent them properly. I'm calling it as x hat. I'm calling this as y hat. I'm calling this as z hat. All these vectors are lying on the different axes that we have in your three-dimensional coordinate space. This is your x-axis, and this is your y-axis, and this is your z-axis. So now you can go about representing any given vector here. I'm calling it as v bar with specific set of components or coordinates, right? The coordinates can be any given numbers, right? So 3 here would represent that it's 3 points away from the origin point here. That is 1, 2, and 3. 2 here for the second coordinate signifies that it's 2 points away from origin on the lines of y-axis and 1 point away from origin on the lines of z-axis. X hat, y hat, and z hat here are the three different vectors, unit vectors that are lying on x-axis, y-axis, and z-axis. So x hat basically is a unit vector, y hat and z hat, all three of them are unit vectors, and hence we have represented these vectors using hat rather than using bar like what we have represented for v bar. So all these three basis vectors define the vector space here. Any vector that we are going to define like v bar is being represented, or the components or coordinates of this particular vector is being represented with respect to these three basis vectors here. So all these unit vectors are called as basis vectors. So your vector coordinates or vector components are defined based upon these basis vectors like x hat, y hat, and z hat. Right? We also have understood that all these three of them are nothing but your unit vectors. A vector is said to be a unit vector only when its magnitude is equal to 1 or length is equal to 1. Right? We also have understood the fact that all three of them are perpendicular to each other, and hence they are orthogonal vectors. When vectors are perpendicular to each other, they are called, or they are said to be, orthogonal in nature. And when all these three vectors which are perpendicular to each other are unit vectors, then they are called as orthonormal vectors. Let's understand the difference between unit, orthogonal, and orthonormal properly. Unit vector is a vector which has got a magnitude of 1. Orthogonal vectors are 2 or 3 different vectors which are perpendicular to each other. They are also called as orthonormal vectors when basically each one of its magnitude is equal to 1. Alright. The same vector here can be represented in terms of other basis vectors altogether, right? So for instance, this is your E1 hat, and this is your E2 hat, and again this is your E3 hat. All these E1 hat, E2 hat, E3 hat would define all the vectors that are present in your vector space again, right? You can also define your V bar in terms of, or with respect to E1 hat, E2 hat, E3 hat instead of X hat, Y hat, and Z hat. When you represent your V bar or the vector V with respect to these three new basis vectors, then you will no longer have the same coordinates or same components, but rather you will have different components or different coordinates, because now you are looking at how far away it is from each one of these new basis vectors. And that's the key distinction. So every single vector will still remain intact, but the coordinates or components will change when you change your basis vectors altogether. We'll also learn about change of basis in our future lectures, but for now let's confine ourselves in understanding about your vector representation with respect to the different basis vectors that we have. All right, if we have understood it thoroughly, then let's move on to defining this particular vector v bar that we have, or vector v that we have, by vx multiplied by x hat plus vy y hat and vz z hat. We know that x hat, y hat, and z hat are the basis vectors here. So when we have the basis vectors in place, you can rewrite your vector in the component form, which is your column vector vx, vy, and vz. This is your component form. That is, you have coordinates that are being represented as each element in your column vector. All right. The magnitude of this particular vector is given as square root of vx square plus vy square plus vz square. I'm not getting into details on how you derive this particular formula because this is derived by using Pythagoras theorem, which is basic high school math. So I do not want to revisit this. I expect each one of you to know about how you deduce the hypotenuse value in a right angle triangle. All right, perfect. With this context in mind, let's go about looking at how you perform various operations on given vectors. Of course, you can perform addition of two different vectors. You can go about looking at subtraction of two different vectors, how you subtract two different vectors, and also look at how you multiply different vectors here. So when you add up two different vectors, let's say for instance, this is your vector A and this is your vector B. So your new vector A plus B would be this resultant vector. How is it going to be the resultant vector is what we'll learn thoroughly in some time. Let's bear with me that whenever you are trying to move away from this particular point here, right, in this direction, which is your A bar, and again from here in this particular direction, that is B bar. So now you have traveled from this particular point A to B. A new vector joining AB would be same as traveling from this particular point A through A and B vectors here, and hence you have this A bar plus B bar, which is again the sum of two different vectors like A and B that you have already represented here. Let's learn about it thoroughly in some time. Similarly, we have subtraction operation. We also can multiply any given vector, that is A bar, with any given scalar quantity. Scalar quantity is any quantity alpha here. So let's say that alpha value is 2 here. Then obviously you have scaled your given vector by 2a, right, or 2a bar. You can also scale any given vector by 3 times its original magnitude just by multiplying a given scalar quantity to a given vector that we already have. Combining these two vectors a bar and b bar with this particular scalar quantity in place, that is alpha a bar plus beta b bar, is nothing but linear combination of vectors. We call it as linear combination of vectors. Of course, you have combined or you have added a bar and b bar scaled by a particular factor called alpha and beta here, and hence it's called as linear combination of vectors. We are going to discuss about linearly combining different vectors much later in this course of linear algebra. We are going to solve the system of linear equations and try and understand how you deduce different parameter values, but not now. All right. So let's understand a little further about how you add two different vectors here. Let's say that this is your vector v bar and this is your vector u bar. For simplicity, you can call it as vector v and vector u. Now, of course, you can also draw another vector like this, which is actually parallel to this particular vector v here, and also is of same magnitude as that of v, and hence you can also call it as v because it's parallel to this particular vector because the direction is same and also the magnitude is same. When there are two vectors whose direction and magnitude are matching, then they are essentially similar or same vectors. Right? Of course, I did mention to you that you can draw another vector to this particular terminal point here now and call it as v bar plus u bar, right? Because from this particular point here, now you are traveling through this vector u and also vector v, and you can also travel to the same terminal point. This is your terminal point now, right? You can also travel to the same terminal point right from this initial point by drawing a new vector altogether and call it as u bar plus v bar. When I click upon this show some checkbox here, we understand that that's what we have derived. Whenever I'm going to change this particular direction of this particular vector, say for instance, I have changed the direction of this vector like this. And now you go about drawing a parallel vector. That means to say you are drawing a new vector with the same direction as that of your vector v here. And you also have the same magnitude as that of v, and hence this is analogous to your vector v. Of course, I did mention to you that you can draw a new vector directly from this initial point to this terminal point, right? Which reaches this terminal point either by v and u or by this new vector, which would be obviously same as that of reaching or traversing through u and v. And hence I can call this new vector as u plus v. That is sum of both these vectors u and v that we have. Say for instance, your vector v has got the coordinates of 3, 2 and 1, and your vector u has got the coordinates of 1, 0 and 2. Of course, the sum of these two vectors could be a resultant column vector with 3 plus 1, adding the corresponding elements here 3 plus 1, 2 plus 0 and 1 plus 2. That would result in 4, 2 and 3. And this is as simple as that. And you have also geometrically understood how you can interpret the sum of two different vectors that we have. Okay. Let's also understand how you can interpret subtracting two different vectors that you have. Let's say for instance, we have two different vectors u and v again. I'm sliding this to illustrate u minus v. Now you understand that whatever vector v that you have, and just opposite to whatever vector, the opposite direction to whatever vector v that you have is nothing but your negative v, isn't it? And let me slide through this completely. Now we also can understand that whatever vector v that you have, a parallel vector that's joining the tip of vector u with the same magnitude as that of v and opposite direction as that of v could result in minus v, isn't it? So the direction is opposite and hence we have this negative sign here, but the magnitude is same, and hence we are still calling it as a vector v here, isn't it? Of course, when you are traversing to this particular terminal point through u and minus v, you draw a new vector here which reaches the same terminal point as that of traversing through u and minus v. I can call it as u minus v, and that's it. Similarly, you can go about looking at how you deduce the resultant vector for v minus u. Just like you have minus v for a new vector that you have looked at, you also have minus u for a corresponding vector v u that we have. So let's draw a new vector from this particular terminal point of v in the direction opposite as that of u. Then you will have this negative sign, but same magnitude would result in the same u vector here, right? Of course, you can reach to this particular terminal point by traversing through v and then minus u, and hence we can call this new vector that we have drawn from the initial point to terminal point directly as v minus u, right? I believe we have pretty much understood how you can interpret these findings that we have for subtraction as well as addition of two different vectors that we have. All right. So let's revisit this particular discussion again here. We have this particular vector called u. All right. And I'll draw a new vector from this particular terminal point of v, which is of same magnitude as that of u, but in a direction opposite, right? So this is traversing towards left, and I'm drawing a new vector here which is traversing towards right, but of same magnitude as that of u here, and hence I'm calling it as minus u. When you take this route of this initial point to this particular terminal point here, that is traversing through v and then minus u, then you have looked at reaching this particular terminal point through v and minus u, and then you can come up with a new vector altogether which is same as that of traversing through v and minus u, and hence I can call this as v minus u. I believe we have pretty much understood how we can come up with a new vector in the same vector space, which is subtraction of two different vectors that we have. We also have looked at how you can come up with addition of two different vectors that we have. Let's say for instance we have this particular vector a here, and then there is another vector called b here. Of course, this could be your a plus b because this is your initial point. This is your terminal point. You are traversing through a and b, and you can come up with a new vector altogether which is same as that of traversing through a and b, and call it as vector a plus vector b, right? On the same lines, you might have two different vectors which are traveling in the same in a similar direction, and but of differing magnitudes altogether. Of course, you can come up with something like this, which a new vector altogether, which basically is parallel to this particular vector b and is of same magnitude as that of b. And of course, you can come up with a new vector altogether here. You can come up with a new vector altogether here, which is same as that of traversing through a and b when it travels from initial point to the terminal point. And that's how you can come up with sum of two different vectors, and that's how you can interpret the new vector, which is a sum of two different vectors in the given vector space that we have. Of course, there is a entirely different operation that you can perform, that is your vector multiplication. There are two different multiplications or products that are possible, one of which is dot product of two different vectors, and the other one is cross product of two different vectors. We are going to pretty much use dot products a lot, but not going to use cross product so frequently, and hence I'm not going to cover this cross product as such. However, I'm going to help you out if you are necessarily looking at learning about cross product in depth. All right. So we are going to extensively cover about what dot product is and how you take the product of two different vectors that you have, vector A dot vector B, or probably vector U dot vector V dot vector U, whatever it is, whatever two vectors that you are considering. What is the resultant value of dot product of those two vectors is what we are going to thoroughly discuss in our subsequent session. So this should be equal to magnitude of vector V and magnitude of vector U multiplied by cos theta, right? Which is also equal to Vx Ux plus Vy Uy plus Vz Uz for three-dimensional vector space, and this is in your component form. This again is a dot product of two different vectors v and u in component form. All right. And in the subsequent session, we are going to learn more about dot product of these two vectors. And that's all in this particular session. And thanks for watching.